The objective of this lecture is to provide the first part of the study of coplanar impulsive orbital transfer. This lecture focuses on fundamental concepts and the Hohmann transfer. This lecture will be divided into the following parts. First, the basic concepts of orbit transfer are provided. And then the discussion will turn to the constructs of impulsive orbit transfer. And then the lecture will turn to two impulse coplanar orbit transfer. And finally, a detailed study will be provided of the most basic two impulse coplanar orbit transfer called the Hohmann transfer. So let's start with the basics of orbit transfer. So until now, the focus has been on the motion of a spacecraft moving in a particular orbit. Now, in this study, there was no changing of the orbit. So, in this previous analysis, the orbit was fixed, meaning that we weren't going between orbits. But now, attention is turned to changing the orbit of a spacecraft. The process of changing the orbit of a spacecraft is called orbital transfer, or more simply, orbit transfer. So orbital transfer is defined as follows. It's a sequence of one or more maneuvers that change the orbit of a spacecraft from an initial orbit to a terminal orbit. Now, in this first part of the study of orbital transfer, we will be dealing with transfers between orbits about the same body, in which case the maneuvers will be propulsive. So we will be dealing with propulsive orbital transfer. And propulsive orbital transfer is when the maneuvers are due to thrust applied to the body or applied to the spacecraft. Now recall from the basics of rocket dynamics the impulsive thrust approximation. Now, the impulsive thrust approximation was one where the velocity could be changed instantaneously using an impulse where the thrust was infinite over zero duration. So the impulsive thrust approximation looked as follows: is if I have a spacecraft moving in an orbit, and at some point the velocity is VI, and I call it VI minus, and instantaneously I change the velocity to some new velocity, VI plus, then that instantaneous change leads to an impulse, which is referred to as delta V. So it's delta VI, which is equal to VI plus minus VI minus. So delta VI is equal to VI plus minus VI minus, and it's an instantaneous impulse. And for completeness, I is an inertial reference frame. Now, this instantaneous impulse is what's going to be used for the model that we're going to develop for orbit transfer. So in this study, we will develop the basics of impulsive orbit transfer, or impulsive orbital transfer. So impulsive orbital transfer is when all propulsive maneuvers are approximated as instantaneous impulses. So the focus of this study is on impulsive orbital transfer. So now we're going to get more specific, and we're going to focus on coplanar impulsive orbital transfer between circular orbits. So by coplanar, we mean that the initial and terminal orbits lie in the same inertially fixed plane. And when we say we're going between circular orbits, the idea of circular means that the initial and terminal orbits are circular. And of course, we've discussed earlier that we're dealing with orbit transfer about a single body. So we're not changing between bodies. Our central body remains the same for this orbit transfer. Now, the most fundamental type of impulsive orbital transfer is what's called a two-impulse orbital transfer. Now, as the name might imply, a two-impulse orbital transfer accomplishes the transfer using exactly two instantaneous impulses. And this class of two-impulse orbital transfers will be the focus of the remainder of this lecture. So now let's consider a two-impulse orbital transfer between coplanar circular orbits. So let's start this discussion off with a diagram. So on this diagram, I have two orbits. The first orbit is my initial orbit, and it has radius r1. The second orbit, which is the larger orbit, is the terminal orbit, and it has a radius r2. Now, in order to be able to transfer the spacecraft between these two orbits, using exactly two impulses, there must be a transfer orbit that intersects both orbits. So I'm going to draw that transfer orbit as an ellipse because it's an elliptic transfer orbit. So here's my elliptic transfer orbit. Now that elliptic transfer orbit, you can see, has to be such that it intersects the initial orbit, and there's a point which I'll label as the point of intersection between the initial orbit and the transfer orbit. And it also has to intersect the terminal orbit. Now you can see that as the spacecraft is moving on the initial orbit, at the point of intersection with this elliptic transfer orbit, prior to the application of the first impulse, the velocity of the spacecraft has to be in the direction that I've drawn with the arrow, and that velocity has to be v1 minus I, and it's tangent to the initial orbit. Well, after the application of that first impulse, the velocity now has to be pointed in the direction tangent to the transfer orbit. So that velocity is v1I plus. And you can see from the diagram then that delta v1 has to be the impulse that takes me from v1I minus to v1I plus. So this is delta v1I. Now similarly, when I intersect the second orbit or the terminal orbit, I'm on the transfer orbit, and the velocity has to be tangent to the transfer orbit, and that velocity is v2I minus. And after the application of the second impulse, the velocity is going to be v2I plus. Which means that delta v2I has to be the vector from v2I minus to v2I plus. So we have two impulses here. We have delta v1I and we have delta v2I. And you can see that these 2 points that I've labeled here, these are points of intersection. Of the transfer orbit with the initial and terminal orbits. Now, let's look at the conditions under which a two-impulse transfer of the kind that I've drawn is possible. So these are the conditions required for a two-impulse coplanar circle-to-circle transfer. So first, it can be seen that the periapsis radius of the transfer orbit, or the elliptic transfer orbit, has to be less than or equal to r1. So that implies that p over 1 plus e has to be less than or equal to r1 because rp is equal to p over 1 plus e. So that implies that p has to be less than or equal to 1 plus e times r1. So that's the first condition. So also, it can be seen that the apoapsis radius of the transfer orbit has to be greater than or equal to r2. So that implies that p over 1 minus e has to be greater than or equal to R2, and that's because RA is equal to P over 1 minus E, from which we obtain that P has to be greater than or equal to R2 times 1 minus E. So therefore, the parameter, also the semi-lattice rectum, of the transfer orbit must satisfy the condition that P has to lie between R2 times 1 minus E and R1 times 1 plus E. So these are the conditions required in order to be able to accomplish a two-impulse coplanar circle-to-circle transfer. So we will now focus on the most basic two-impulse orbit transfer between coplanar circular orbits called the Hohmann transfer. Now going back to our diagram, the Hohmann transfer has the following form. Once again, the transfer orbit is an ellipse, and it's an ellipse in such a way that it is tangent to both the initial and the terminal orbit. It's tangent to the initial orbit at the point of application of the first impulse. So that's at the bottom of this diagram. I have this first impulse, and it causes the spacecraft to move on an elliptic transfer orbit until it achieves tangency with the second orbit. So the first impulse, which is delta V1, is applied tangent to the initial orbit in such a way that the spacecraft now is on an elliptic transfer orbit that intersects the final orbit or the terminal orbit in such a way that the second impulse, delta V2I, is applied tangent to the second orbit. So once again, we have the initial orbit here. We have the terminal orbit. And then this is the transfer orbit. So now we make the following two key observations about the structure of the two impulses for the Hohmann transfer. The first is that delta V1I is applied tangent to the initial orbit and is located at the periapsis of the transfer orbit. The second observation is that delta V2I is applied tangent to the terminal orbit and is located at the apoapsis of the transfer orbit. Now the structure of these two impulses can be seen in the diagram as follows. So O is the focus, And the distance from O to the location of the first impulse is r1. And that distance is equal to the periapsis of the transfer orbit. Similarly, the distance from O to the location of the second impulse is r2, and that's the apoapsis of the transfer orbit. And just for completeness, this transfer orbit is half of an ellipse, where the starting point on the transfer orbit is periapsis and the ending point on the transfer orbit is the apoapsis of the transfer orbit. So now that we've seen all this structure, the next thing to do is to determine the two impulses for the Hohmann transfer. Now, in order to determine the two impulses for the Hohmann transfer, the following terminology will be used. First is that the magnitude of V1 minus I will be denoted V1 minus. And similarly, the magnitude of V1 plus I will be denoted V1 plus. So those are the two velocities before and after the first impulse is applied, and then I've taken the magnitudes of the two of them. So in a manner similar to that, V2 minus I in magnitude will be denoted V2 minus, and V2 plus I in magnitude will be denoted V2 plus. So what we're going to do is we're going to use the terminology that was just stated together with the structure of the impulses to determine the total impulse for the Hohmann transfer. So here's a key observation, which is that each impulse in the Hohmann transfer is applied tangentially. So what that means is that the direction of V1 minus I and V1 plus I is the same, and it implies that the direction of V2 minus I and V2 plus I is the same. So we now can simplify things quite a bit, because what that means is as follows. Is suppose I say let U1 be the direction of V1 minus I and V1 plus I. And I let U2 be the direction of V2 minus I and V2 plus I. So then we know that V1 minus I is equal to V1 minus, which is its magnitude, times its direction, and V1 plus I is equal to its magnitude, which is V1 plus times its direction. And similarly, V2 minus I is equal to V2 minus, which is its magnitude, times its direction. And then V2 plus I is equal to V2 plus, which is its magnitude, times its direction. So then, the magnitude of delta V1I is equal to the magnitude of V1 plus I minus V1 minus I, which is equal to the magnitude of V1 plus times U1 minus V1 minus times U1. But that implies that the magnitude of delta V1I is equal to the absolute value of V1 plus minus V1 minus, because it's multiplied by the magnitude of u1, but that's just 1 because u1 is a unit vector. And similarly, the magnitude of delta v2 I is equal to the magnitude of v2 plus I minus v2 minus I, which is equal to the magnitude of v2 plus times u2 minus v2 minus times u2, which implies that the magnitude of delta v2I is equal to the absolute value of v2 plus minus v2 minus. So we need to just determine these magnitudes of these four speeds, and we will be able to determine the total impulse. So determine v1 minus, v1 plus, v2 minus, and v2 plus. So let's look at this picture again. So we can see that given that the initial radius is r1 and the final radius is r2, and the elliptic transfer orbit has its periapsis at r1 and its apoapsis at r2, that the semi-major axis of the elliptic transfer orbit is given as follows. Is A is equal to R1 plus R2, all divided by 2. Now once we have that, we can actually determine these four speeds. So now recall from earlier the V's Viva equation. Which is that v squared is equal to mu times 2 over r minus 1 over a. Well, that implies that v is equal to the square root of mu times the square root of 2 over r minus 1 over a. And now we can use this result to be able to determine these four speeds. So first, v1 minus, because the spacecraft is initially in a circular orbit of radius r1, is just equal to the square root of mu over r1. v1 plus is equal to, now let's use this result from the V's Viva equation, the square root of mu times the square root of 2, all divided by r, but r is equal to r1 because we're applying an instantaneous impulse, so the position doesn't change, and it's minus 1 over a, where a is the semi-major axis of the transfer orbit. So as a result, we get that v1 plus is equal to the square root of mu times the square root of 2 over r, 1, and then we've got minus 2 over r1 plus r2, which can be simplified as follows. We get the square root of mu times the square root of 2 times r1 plus r2 minus 2 times r1, all divided by r1 times r1 plus r2, where I've just put everything over a common denominator. And that implies that v1 plus is equal to the square root of mu, and the numerator in the square root simplifies to, you got 2r1 minus 2r1, you get 2r2, all divided by r1 times r1 plus r2, which is equal to the square root of mu over r1 times the square root of r2, 2r2, all divided by r1 plus r2, which gives that v1 plus is equal to the square root of mu over r1 times the square root of r2, all divided by a. So now we can actually figure out this first, the magnitude of this first impulse. So we then have that the magnitude of delta v1I which is equal to the absolute value of v1 plus minus v1 minus, is equal to the absolute value of the square root of mu over r1 times the square root of r2 over a minus the square root of mu over r1. But now we can factor out the square root of mu over r1 because it's positive, and we're left with the absolute value of the square root of r2 over a minus 1. But note that r2 is bigger than a, and that's because a is equal to the average of r1 and r2 over 2 because it's the semi-major axis of the transfer orbit. So as a result, the absolute value can be dropped and we can just leave it without the absolute value, and we get the magnitude of delta v1I is equal to the square root of mu over r1 times the square root of r2 over a minus 1. Now, for simplicity in the future, we're going to just replace the magnitude of delta v1 as follows. So we're going to say let delta v1 equal the magnitude of delta v1I, which we now know is the square root of mu over r1 times the square root of r2 over a minus 1. So next we're going to follow a similar procedure in order to determine the magnitude of delta v2. So next we have v2 minus is equal to, well, now let's be careful, because we're at the apoapsis of the transfer orbit, so it's the square root of mu times the square root of 2 over r2 minus 1 over a, because the apoapsis of the transfer orbit is r2. And v2 plus is equal to the square root of mu over r2, because after we apply the second impulse, we're in a circular orbit of radius r2. So now we can apply a similar process to simplifying v2 minus as we did to simplifying v1 plus for the first impulse. So we have v2 minus is equal to the square root of mu times the square root of 2 over r2 minus 1 over a. But that's equal to the square root of mu times the square root of 2 over r2 minus 2 over r1 plus r2, because a is equal to r1 plus r2 divided by 2. So that implies that v2 minus is equal to the square root of mu times the square root. We put this again over a common denominator. We have r2 times r1 plus r2, and we have 2 times r1 plus r2 minus 2 times r2, which is equal to the square root of mu times the square root of r2 times r1 plus r2, and in the numerator we have 2r1 plus 2r2 minus 2r2, so we get 2r1. So that implies that v2 minus is equal to the square root of mu over r2 times the square root of 2r1 all divided by r1 plus r2, which is equal to the square root of mu over r2 times the square root of r1 all divided by a. So then, using that result, we have that the magnitude of delta v2I is equal to the absolute value of v2 plus minus v2 minus, which is equal to the absolute value of the square root of mu over r2 minus the square root of mu over r2 times the square root of r1 all divided by a. But now we can factor out the square root of mu over r2 out of this result because it's positive, and we're left with the absolute value of 1 minus the square root of r1 all divided by a. But notice that R1 is less than A. And that's again because A is equal to R1 plus R2 over 2. So it has to be bigger than R1. So that implies that the square root of R1 all divided by A is less than 1. So as a result, the magnitude of delta V2I is equal to the square root of mu over R2, and we can drop the absolute value. We get 1 minus the square root of R1 all divided by A. And in a manner similar to what we did for the first impulse, we'll say let delta V2 equal the magnitude of delta V2I, which is then equal to the square root of mu over R2 times 1 minus the square root of R1 all divided by A. So then, the magnitudes of the two impulses for the Hohmann transfer are given as delta V1 is equal to the square root of mu over R1 times the square root of R2 over A minus 1, and delta V2 is equal to the square root of mu over R2 times 1 minus the square root of R1 all divided by A, which implies that delta V for the Hohmann transfer, which is equal to delta V1 plus delta V2, is equal to the sum of these two impulses. So we have the square root of mu over R1 times the square root of R2 over A minus 1, and plus the square root of mu over R2 times 1 minus the square root of R1 all divided by A. Now, it is useful to express the total impulse of the Hohmann transfer in terms of the ratio of the radii of the initial and terminal orbits. So in order to do that, we're going to say let R equal R2 over R1. So that's the ratio of the radii of the initial and terminal orbits. So then we have that delta V1 is equal to the square root of mu over R1 times the square root of R2 over A minus 1. Now let's rewrite that using this ratio. So we can see that that's equal to the square root of mu over R1 times the square root. So I'm going to divide the numerator and denominator of this square root by R1. So I get R2 over R1 all divided by A over R1 minus 1. But that's equal to the square root of mu over r1 times the square root of r, because r2 over r1 is r, all divided by r1 plus r2, all divided by 2r1 minus 1. So then, delta V1 is equal to the square root of mu over r1 times, well, if we bring the 2 to the numerator, we get 2r all divided by r1 plus r2 all divided by r1 minus 1, which is equal to the square root of mu over r1 times the square root of 2r all divided by 1 plus r2 over r1, which is just r, minus 1. So that's delta V1 expressed in terms of the ratio r. So next we're going to do the same thing with delta V2. Now delta V2 is equal to the square root of mu over r2 times 1 minus the square root of r1 over a. So what we're going to do to get this thing in terms of the ratio r is we're going to make this the square root of mu over r1. We're going to get the same factor in front as we did for delta V1 times the square root of r1 over r2, and then times 1 minus the square root. And again, I'm going to divide the numerator and denominator by r1. So if I divide the numerator by r1, I just get 1. And then I get a over r1. Now this is equal to the square root of mu over r1, but r1 over r2 is 1 over r, so I get the square root of 1 over r, and then what I'm left with inside the parentheses is the square root of 1 all divided by r1 plus r2 all divided by 2r1. So therefore, delta V2 is equal to the square root of mu over r1 times the square root of 1 over r times 1 minus the square root, and again I'm going to bring the 2 to the top, and I've got 2 all divided by r1 plus r2 all divided by r1, which is equal to the square root of mu over r1 times the square root of 1 over r times 1 minus the square root of 2 all divided by 1 plus r, because r1 divided by r1 is 1 and r2 divided by r1 is r. So now I have both impulses in terms of this ratio. So rewriting both impulses, we obtain delta V1 is equal to the square root of mu over r1 times the square root of 2r over 1 plus r minus 1, and delta V2 is equal to the square root of mu over r1 times the square root of 1 over r times 1 minus the square root of 2 over 1 plus r. So now, let VC1 equal the square root of mu over r1. And that's the initial circular speed. So what we can do then is we can write these both in terms of the initial circular speed. So we then have delta V1 is equal to VC1 times the square root of 2r over 1 plus r minus 1, and delta V2 is equal to VC1 times the square root of 1 over r times 1 minus the square root of 2 over 1 plus r. Now we can add these together, and then we can divide through by VC1. So we can do that in either order. So then delta V1 divided by VC1 is equal to the square root of 2r over 1 plus r minus 1, and delta V2 divided by VC1 is equal to the square root of 1 over r times 1 minus the square root of 2 over 1 plus r. So then the total impulse normalized by VC1 is given as delta V Hohmann divided by VC1 is equal to, well, it's the sum of these two. So it's the square root of 2r all divided by 1 plus r minus 1 plus the square root of 1 over r times 1 minus the square root of 2 over 1 plus r. And just for completeness, we'll put parentheses around this so we know that those two terms are associated with the first impulse. So this last expression provides a way to characterize the total impulse for the Hohmann transfer, first normalized by the initial circular speed, and then in terms of the ratio of the radii of the final circular orbit to the initial circular orbit. It's a universal way to be able to write everything in terms of the fewest parameters possible. So that's why we actually came up with this expression. So now the last part of the study of the Hohmann transfer is the transfer time. Now, in order to be able to determine the transfer time, it's useful to look back on the diagram that was drawn earlier. Now, it can be seen from the diagram that the transfer orbit is exactly half of an ellipse, and the semi-major axis of the transfer orbit was r1 plus r2 divided by 2. And that's the semi-major axis of the transfer orbit. Now, because the transfer orbit is exactly half of an ellipse, we know that the orbital period of the transfer orbit, if it were a full ellipse, would be equal to 2 pi times the square root of a cubed over mu. So then, because the transfer orbit is exactly half of an ellipse, the Hohmann transfer time is given as T sub h is equal to pi times the square root of a cubed over mu. So again, we can see the transfer time on the diagram as follows. So T sub h is equal to pi times the square root of a cubed over mu, and that's the transfer time. And that takes us to the end of the study of the Hohmann transfer. So that takes us to the end of this lecture, and we can summarize this lecture as follows, which is first, we provided the basic concepts of orbital transfer. And next, we described impulsive orbital transfer. And then we got more specific and discussed two impulse coplanar orbital transfer. And finally, the last part of this lecture, we provided a detailed analysis of the most basic two-impulse coplanar orbital transfer called the Hohmann transfer. Now, the results of this lecture are the building blocks for what's going to happen in the future when we describe more complex orbital transfers. The Hohmann transfer is the basis for many of these transfers, and so it's important that we understand the Hohmann transfer well before we move on to more complex orbital transfers. But we'll end this lecture here.